Alrighty, so welcome everybody to my talk where we're going to mostly not mention monads. My name is Beau Lyddon. I am a managing partner at a company called Real Kinetic based out of Boulder here. We do consulting, work with a lot of teams, help them build stuff. And in this presentation, I'm going to focus on strongly typed functional languages, mostly in the ML family. So these kind of languages. Does anybody here have experience with these languages at all? Okay, so this could be a little basic, I don't know. Although all of these concepts will apply to functional languages and even non-functional. So why am I doing this? Because I fundamentally believe the world would be better if we embrace functional concepts. I've been in the industry 20 plus years now, and I've worked at large companies. I've seen the messes, but going back to this morning's keynote, I embrace everything he said, and I think functional is one of our ways out of the messes we've been making. And to do that, we need to start shipping more code based around functional programming. And this is not going to be a direct teach you the language presentation, by the way. It's more of a get comfortable with this stuff. It's definitely more of a kill the FUD presentation. My goal here is to remove the barriers that a lot of people seem to hit before getting into some of these languages. And this all comes from my own experience attempting to learn these languages. I wanted to learn functional many years. Even started coming to this conference when it was first starting, not having any experience. And I still was struggling to kind of get into it. And a lot of that was because I still probably have some imposter syndrome from a lacking mathematics background. I do not have much of a mathematics background at all, so I always felt like, well, if you don't know math, you can't do this stuff. I also struggle to learn from programming books. I don't really do well with books. And anytime I normally would learn by just getting into code, existing code, working my way through it, figuring it out. And I always seem to struggle, especially with languages like Haskell, because everything seemed just so advanced. And what I was kind of realizing is I was struggling to figure out, is it because of these languages are advanced? Or is it the syntax? Why am I struggling so much to get into them? So one thing I do want to make clear, this is not going to be an anti-terminology presentation. I was that person and I was very wrong. I was that one who would make fun of people that used all the mathematical terms. And then I started working in distributed systems and realized I was an idiot. The terminology can be quite helpful. It can be a upfront burden blocker. So that's part of why I'm doing this, is to help get around it. But hopefully as you get going, you'll realize that terminology is good. So instead, I hope to show you don't actually need to understand all the terminology to build these systems and get them into production. You don't need to be great at math or even go through books. You can be productive in all of these languages and get all of the benefits without knowing any of that. And this is also why I'm going to focus today on Elm. Elm is a compiled to JavaScript, mostly front end, in the browser-based language. It can do others, but for the most part, it focuses on that. And Elm is kind of meant to be the accessible typed ML language. It's designed for you to get work done and shipped to production. And if you leave this presentation excited about Elm, I guarantee you can go and ship stuff tonight. I'm not kidding. This is why I got into it. I started a project with one of my partners, downloaded all the JavaScript nonsense, Redux at the time, literally couldn't get it to compile. And I'm like, this is annoying. Went for a walk, listened to a podcast. It's the Redux creator. He says, well, I stole everything from Elm. And I'm like, okay. So I went home, installed Elm, and shipped that night. I was like, oh, that was night and day from what I was doing in JavaScript. So Elm it was. So part of the reason Elm can do this is it sacrifices some power to allow it to be more accessible. They purposely avoid the non-common mathematical terms. They will use the more verbose, maybe more beginner-friendly language. But hopefully once you've done some stuff in Elm, it will actually drive you to want to learn more and dig deeper. That's definitely what's happened to me. I actually spend more time in pure script and Haskell than I do Elm, but without Elm, I'm not sure if I would have. And whether you do any of this, I still actually spend a lot of my time for the companies we work for and whatnot writing in other languages. I write everything from a functional perspective. And that's actually part of the reason I got into it too, is doing distributed systems. I was writing all my Python using immutable variables and voiding things like state because I wanted to keep my sanity. So fair warning, once you start, you might not stop, but let's get going. So the first hurdle for most people is syntax. And we're going to go through this pretty quick, because I want to get to the fun stuff at the end. So I personally find, I learned this from doing a lot of code reviews over the years, I think it's important just to see the syntax, pattern match, get your brain used to it. So that's kind of what I'm going to try to do here, is go through it quickly, so you can, hopefully you'll just start to get comfortable with the syntax. So we're going to make a quick counter in Python. This obviously wouldn't actually work because I don't call in something like Django. But hopefully this is relatively straightforward. I can actually even show quickly, hopefully, what we're building here. I can figure out what way my browser goes. There we go. Oh, man. Ooh, that is zoomed in a little bit much. The dumbest little thing, right? This guy. That's what we're going to build. Get my cursor back. There it is. So we just got this thing that we're going to increment and decrement, an update function, some HTML. And now let's look at this in Elm. And part of the reason I did the Python is I kind of want to show the structure is the same. This is one of the first kind of things that I realized quickly when I got into these languages, is it kind of felt a lot like Python. Like, even when I looked at it, it looked a lot like Python. So you can kind of see going back and forth, the structure feels the same. Back to that pattern thing, it felt kind of familiar. But one thing you'll notice quickly, there are no types, and this is supposed to be typed languages. But if you're used to these languages, you know that they are not actually required, they're inferred. It is definitely recommended that you annotate your code with types. So let's annotate our code, and let's annotate our Python code with types. This is how we annotate Python code with types. We put it in the comments. Super useful. It is actually super useful in Python, because this is the only sanity you'll have, is to put it there. There is kind of standards for it, but not really. Most people just kind of do something where they get some types in there. Now let's do the same thing in Elm. And if you kind of look at what we did previously, right? We have this code. It's actually kind of not even all that different than what we did in Python. We just annotated the code. We didn't change the structure of the code. We didn't do any of that. We just annotated it kind of in the same way we stuffed it in the comments of the Python code. It doesn't actually change anything. It's almost a bit like documentation. And I will walk through into detail if you don't know what's going on here. So once again, that's what it looks like. So let's go through that now and start with type definitions. So the last type in this, if you're not familiar with kind of the ML style syntax, Haskell syntax, the last type, so in that beginning one, thing, int, takes no arguments. The last type is int. It's just going to return an int. So we're just assigning 0. That forever is 0, which is forever an int. That function right below it, add, takes 2 ints and returns an int. This sadly, like for a lot of people, including myself, took a long time to get used to the arrows and why isn't there something that makes it obvious the last one is the return type. But you'll kind of get used to that, and I'll show you later why that's important. But takes 2 ints, returns an int. That's all that's saying. We can also alias our types. So we can take an int and just call it things if we want to. This actually makes things readable. So you still get the compile safety of it's going to make sure it's an integer, but you can now make it a little more readable and familiar to you. So later, instead of just seeing int, you can go, oh, that's that thing. It just so happens to have the same characteristics of an integer. So this helps with readability again. We also have this thing called sum types or union types. So that bar in the middle is basically, you can read that as or. So it's saying this type of message is increment or decrement. And we can have as many of those options as you'd like. So we can have cars with Mustang or Camaro or Taurus or Fit or Focus, and we keep adding. The Boolean, obviously, there's 2, true or false. Just saying this type bool is either true or false. So why is it called a sum type? Because you can find the total number of possible values by just adding those together. So bool has 2 possible options, false and true, 2. Cars, in this case, has 5. These are a bit like enums in other languages. So like enums in Python look something like this. And this is kinda, not quite the same as a sum type, but it's kinda the same. So if you're used to using something like an enum, you can kind of have a feeling of what it's like to use a sum type. JavaScript is even further away. They have this thing called freeze, apparently. I don't know. I purposely avoid JavaScript. I will have some in here to show it, but this is kind of a reason why. It actually takes quite a bit of code. So that simple little sum type in Elm, it takes about this much code to make one of those in JavaScript. So to even have, this kind of shows you how constraint makes things powerful, right? That thing is so simple to actually make this language like JavaScript, which lets you do whatever the hell you feel like, you gotta have to go introduce this constraint to make it so simple. It doesn't really matter, I'm just more pointing out that like it takes a lot of work to actually get a simple type like a sum type in JavaScript to do that behavior. But if you want to do it, you can go get that code and actually have more kind of proper sum types in JavaScript. One of the big reasons we use these sum types is we like pattern matching in these languages, and sum types and pattern matching really go well together. So what do we mean by pattern matching? So here I'm going to create my own custom Boolean type where I've got my false and my true. And then I create this function handle bool that takes my bool and returns a string. And all we're doing is matching against our values. So that case statement just says, when I get that my bool, if I have a true, I'm going to return a string that says I have my true. If I match against the false, I'm going to return a string that says I'm false. That's all pattern matching is. In these other languages, it's like in Python, you're really just doing if statements. If it's this, if it's this, if it's this, if it's this. You're just matching the structure, right? When you write if statements, you're matching the structure against that. So this is kind of the same way you would do this in Python. Except Python's not very safe. We can do this. We can pass in whatever the hell we feel like in Python, and it'll just return us none. So we do things like this. We say if this or this, else this. Got to handle that sucker. Of course, that usually add that code after you've already blown something up in production. JavaScript, same exact deal. JavaScript does provide switch statements, unlike Python, so it looks a little bit closer to that case statement that we have in Elm. So if you're comfortable with switch statements, you're going to be comfortable with case statements. But there's also nothing stopping us from doing this. We don't have to match all the things. We can just say, we're only going to match true. If you give us false, I guess none again. Which, if you get none in Python and JavaScript, what's the difference between none, false, 0, empty? Oh, God. So let's try this in Elm. We're only going to match one of them. We're only going to handle our true case. Elm will not let us do that. This is why we use these languages. Elm goes, no, you have to cover false. You're not covering all of your cases. So I guess we'll try default. We're going to throw a default in there. No default, so it doesn't have default. What do we use in Elm? We use this underscore. It's kind of saying, think of that as like bottom. It's saying, we're going to catch everything else. All that other crap, we're going to handle it with this underscore. So in this case, we're not going to handle the true, or the false. We're just only going to handle the true, and everything else is going to fall to that underscore. All right, so that's kind of your else, right, if you're thinking ifs again. So what if we do this? We're going to have my true and my false, and just in case, because there could maybe be something not true or false in my data structure. But actually, Elm doesn't let you do that either. Actually, it will let you do this. It'll just say, why are you doing that? Because you're handling the two other cases. So you're good. Get rid of that last statement. And if you've worked in enough code bases, you know too much code is as bad as bad code. So get rid of dead code. Elm's compiler will actually find dead code for you. Code that has no chance of being hit. So delete it. Functions, arrows, partial application, and currying. Sounds much harder than it is. All of these languages have it, and you probably use it all the time. So we're going to take two integers and return an int, or add them together and return it. We've seen this before, add two things, right? But you actually don't have to pass it two things. You can just pass it one thing. This reason I want to go through this is if you're kind of new to this and you're going through these languages, this may be a common thing you're debugging because you forgot to pass an argument to a function and you get this weird statement. You're like, oh God, what is going on? It can look really nasty. It's a very good chance you just didn't give the function you were trying to call all of the arguments you meant to give it. So you'd say, why don't they handle that? Well, this gets into the depths of functional, but there's a lot of good reasons why we actually allow partial application, which is what that was. So we only partially applied all of our arguments. So add two things with a 1, what is it actually happening when we do that? It's returning us another function of int to int. So we had that thing that was int, takes two ints and returns an int. When we give it 1, it actually becomes more like this kind of thing. And in these types, when you see parens around the arrows, what that's saying is a function, right? So So in this case now, when we do that, we're taking a function that takes one argument and returns a function that goes from int to int. So we can actually set that up to a variable. We could say let add to 1 be equal to add to 2 things where we give it 1. And you could kind of read that now as more like, oh, it's more like 1 plus whatever thing I'm going to give it. So you can kind of chain those together. If that's still a little bit out there, let's go through some Python to show the same thing. So this isn't partial application. This is just returning a function. That's how you return a function in Python. You just return a function. So we take a single argument here. We're going to return it. And then we can call it with the 1. Set that with 1 passed into another argument. And now we can call it again and get 2. But Python does actually come with partial application as well. You actually have to import it from their Func Tools. So if you're a Python developer and you want to do a lot of functional stuff, they have a module called Func Tools that has all of the fun stuff we use in these languages buried in there. And one of those is partial application. So again, we have our add 2 things function. But in this case, we're just going to pass it our function, our first argument. Going to partially apply it. And now add to 1 is a function that takes our other argument. JavaScript is a little bit more like our Haskell, where you don't have to use partial. It just automatically does this. Guessing based off JavaScript's design purely by accident. They take in the 2, you can just pass in the 1 argument there, it returns you a function, and then you can call it again. So that's what partial application, currying, and the important part that I want to call out here is higher order functions. What are higher order functions? It's a function that does at least one of the following. Takes one or more functions as arguments, or returns a function as its result. That's all they are when you can pass functions around. Right? Functions that take and or return functions themselves. We'll come back to this later and use it often. It is very important in these languages to get comfortable with treating functions like data themselves. You're going to pass them around just like you would data structures, and you need to be very comfortable with that. So let's go through some more syntax. This is from our earlier example. Hopefully now this is making some sense. We got a message that is either increment or decrement. We're going to pattern match against those. Our model, we know model actually means integer. So we're just adding 1 to our model and returning that. If it's a decrement, we're going to take away 1 and add that. And by the way, to kind of prove the Elm thing again, where's my cursor? That is actually all of the code it takes to run that that I showed you earlier. So that I didn't do any magic or anything. That's all the Elm it takes to do that. We can plus minus. We can go initialize our model with something else, compile it, and just like that, we've got that working. Oh, where did you go again? There he is. This is how that same kind of pattern matching would look in JavaScript. Once again, case statement. It's just going to return that state incremented. Let's look at some HTML. Elm has its own HTML syntax if you're used to React, where they kind of have their JSX thing. A little bit like that, but it's a little more programmatic than that. So you can see we have onClick. So that's an actual button action we're passing into the attributes, just like you would in JavaScript, except we're actually giving it one of our messages there. So that first button, onClick, is going to decrement. The second button, onClick, is going to increment. And that's just all it takes is to trigger those actions in Elm. The other thing I want to call out on that type definition is we have modeled the HTML message. HTML message here is another type alias for virtual DOM node message. And that message, when it has that, it's not capitalized to begin with, that means it could be anything there. They just put message in there to make it a little more readable. It could also just be HTML of A or virtual DOM node of A. If you're coming from type languages like Java, it's basically a generic. Okay? So it's no different than HTML of A, where they use the angle brackets if you're coming from Java or Rust or one of those languages. So it's saying you're going to actually give it a hint later of what type it is. So when we did that earlier, when we said HTML of message, we're saying that's an HTML, and we're giving it our message type up there of increment and decrement. And that's how they know that when you do the onClick to increment and decrement, that's how it wires those together. This is how we would do that, once again, JavaScript with React. So what if we want to store multiple values? We have records. fancy things here. Records are often called product types. I'm just going to go through some of the terminology, so when you hear it, you can go, oh, these things are all the same thing. So why are they called product types? Well, it's a compound type that is formed by a sequence of types and is commonly denoted like this. They correspond to Cartesian products, thus product types. And by allowing you to become named, they become records. So kind of without the naming, they're more like tuples. Once we apply the naming, kind of the tagged attributes, that's when we become records, or in a lot of other languages, they're structs, classes. They're not exactly like those, but once again, similar. And back to the product, you find the total number of options by multiplying, right? Because it's unlike the sum type, it's not either or, you actually have all of these, right? Your record has each one of those tagged values on it. So here's our counter. We're going to have a value and a count on it, and then we're just going to initialize that. So top is our type definition of counter. Bottom is a function to initialize each of those values to 0. How do we get properties off of that? So here we're going to create a function that takes a counter and returns an integer. We're going to return the value, and it's just like a lot of your other languages, just dot notation. Counter dot value gives you back the value on that record. There's also a shorthand accessor. So instead of counter.value, you can actually pass .value. .value is actually a function that takes counter as an object and returns you the value back off of that. That will come in handy later when you start working with things like lists. You want to map those functions over them. So it's the same thing, just a different way to do it. To update a value, it's like this. So we're going to create a function. It takes an int, our counter, and returns a counter. So we take in the new value, our existing counter, and then this syntax chunk here of existing counter and then bar, value equal to new value. That's us just setting that new value to the value property. It will take care of all the other properties we have on the record that we're not actually modifying and leave those there when it recreates. Remember, everything's immutable here, so it's actually going to create a new record. But it's just going to take them all off that other one you passed in for you, only tweak the one you told it to, and apply it. So you'll get back a counter with that value updated, as showed right there. Update value, pass in 10, we get back that with 10 and 0. And multiple values, kind of, it's the same thing, it's just now you're going to start comma splicing those out, right? So you can keep just using commas to update more values if you want to. So here we're going to ensure every time you give us a new value, we actually increase our count. So if we give it 10 below, our value gets set to 10 and our count increases by 1. So in this case, we're actually calling the count off the record we passed in, incrementing it, setting it, off we go. In Python, we would maybe use something like a dict to do this. Looks something like this. It comes with absolutely no safety whatsoever. There's many nasty things we can do with this, but this is probably the closest mapping in Python to a record type. You can also use objects in Python to do something like this. Kind of the same, but this is how you would pass data around in other languages. Similarly, JavaScript would maybe look something like this. I hope also as you're seeing my other examples from other languages, you realize there's a whole lot more character count on those than on the Elm one. And you'll start to realize this over time. It's like, wow, there's just so much less syntax I have to write, yet somehow it is even more powerful. Extensible records. So I'm going to give us 3 different types of records here. You can see the top 2 are just like our other one, but I've added a foo to the one, a bar to the second, and then this 4th record here doesn't have the count and then just has a random string variable. So why are we doing that? Elm lets us alias parts of our data structure. It actually allows you to alias the whole thing like I showed earlier. But we can also say, I only care about a part of it. So what this alias value record is saying is, any record that has a property named value that is an integer maps to our value record type. Literally in a record, as long as it has value of int, you can pass that into anywhere that expects value record A. So you can see down below I have this function that says give me a value record. I'm going to return an int. I'm going to take the value property off of it. So we give it record 2, good. Record 3, good. Record 4, good. All of those had a value property on them. So they pass. Even if we just on the fly define a record, it works. However, those bottom 2 fail. They do not have a value property on them. So it's not going to fail at runtime, by the way. This would have failed at compile time. It said you can't do that. You have to give me a record that has a value of int on it. So why is this important? We can make our code more generic without losing some readability. So now my update code, I can now say, I don't need your very special counter object, right? I just need something that has value so I can increment it. So in this case, I want value and count. So you can give me any record as long as it has value and count, and this function will work. This is how we can write less code but not lose any safety. And of course, we can alias that, so this is how we can not lose readability as well. So now we can say, all right, this is a value record. Yes?
Do you have to, can you have a module that is precompiled and this still works?
What do you mean by precompiled?
Like, say, some the records that had those two fields in there were already precompiled.
Yeah, I mean, you would compile this all together again, right? There's no run time, but if you already, so yeah, let's say you already had like 3 records that existed in your code base somewhere, and you're like, oh, you realize there's a pattern now, and you're like, oh, I'm going to make this to match that pattern instead of building something more verbose. Yes, you can absolutely do that. It literally just matches the structure. It doesn't care about the way you kind of put sugar around it. So it's kind of like, once again, getting back into the mindset of pattern matching. Everything in these languages is about matching the structure. Nulls do not exist. Yay. However, if we can't have a null, we have to have something help us. So we got to kind of think about what does a null mean? It means we have nothing when we might expect something, right? That's usually when you end up with a null or a none in Python, right? I was kind of expecting something, but for some reason it's nothing. So what about a thing called either, right? Maybe it looks like this. It could be either this left thing or this right thing, right? Back to our sum types. This is actually a very common data structure you will use in these languages. However, in this case, it's a little too generic. We know one of them is nothing. Like it's not potentially something. It's literally nothing. So what about maybe something like this? This is another very common data structure you will use in these languages. This one's called result. And here we're saying, well, the one's OK, and the other one's an error. While this is closer, it's not quite the same because it's not an error. It's literally nothing. Like we know it's not even just an error. So maybe we could go with maybe. So maybe we just have our thing, or we have nothing. Right? That's all a maybe type is. Maybe we have something, or we have nothing. That's all that bar is saying is maybe of A means give me any type. It could be equal to just that thing or nothing. And we'll walk through how we actually use that. So here's how you would use it in practice. In this case, if I get a value greater than 0, I'm going to give it back to you. If not, I want to indicate that you gave me something that was not greater than 0. So we're going to take an int and return a maybe. So if our value is greater than 0, I'm just going to give you back the value, but I'm going to put it in that just. That way you know that it's that, right? So nothing. So that you can see down below, if you give me 10, I get back just 10. If you give me a negative, I get back nothing. But now we have this structure to deal with. We have this just, or maybe this maybe, or nothing. And we do not want our code to look like Go code, where you have this everywhere. We don't want that. Thankfully, we have functions and generics. So they said, why not have this thing called with default? We can say, if I have a maybe of A, and I give you this A, you can give me back an A. So what is that doing? It's saying, if I have that maybe, I'm going to pattern match the maybe and match. So it's that case, right, is just saying, if you give me a just, I'm just going to give you back the value. But if you give me a nothing, if that maybe has nothing inside it, I'm going to give you back that default value you gave me. All right, so we can see down below, with default of 10, when we give it just 15, it returns back to 15 because we gave it something. If we give it nothing, we get back the 10 because it says, oh, you had nothing, you gave me a default of 10, I'm going to use your default value. And you can see we can do the same with strings because we have a generic function up here. It's not just int, it's just of A, which means any type we give it, as long as those types align, we're good. It's another function, map. This is where we get a little more advanced because now we see we have the curly braces, so we have a function going in our type. We have something. What's that? There. Oh. Or I didn't mean curly brace, parentheses around the A and B. Sorry. So we take in a function from an A to a B. We take in a maybe, and we return a maybe of A, and we return a maybe of B. So you can kind of, this is another thing to get comfortable, I would actually do this. I would actually read the types out loud. Like as I'm reading that type, just read it out loud, because a lot of times it's that stupid simple in front of your face, and you're overthinking it. So we take in a function that goes from A to B, a maybe an A, and a maybe and a B, and you can start to think about that. All right, I'm going to get back maybe a B, and I'm going to give it a maybe an A, and a function that goes from A to B. Okay, so what we're really saying is we may have an A, and if we do have an A, we want to get back this B. So the function we gives it goes from that A to B. So now we know that's what's actually happening. We're going to take that function, we're going to apply it to that A we give it, if it exists. And the map actually takes care of applying that for you. So you give it just an A, it'll take the A and give you back, or out of it and apply it. And if you give it nothing, it's just going to do nothing. It's going to give you back nothing. Right? So let's actually create an A to B function. We're going to create two of them. So another thing I want to call out is even though it says A to B, there's nothing stopping you from doing A to A, right? Int to int. When it has an A to a B type, that's just saying it can be from one type to another, but it can be from the same type. Right? You can go from the same type to the same type. So we have two functions here. One that goes from int to int, which is actually A to A, but that's fine. That works in an A to B context. And we have an int to string, which does apply to that A to B. Right? Int, there's the A. B goes with string. So now we can run it with map. So our add one, we give it just 10. It takes the 10 from outside of the just. It applies our function that just added literally one value to it, making it 11, and then put it back in the just for us. And now we have just 11. If we give it nothing, it says screw all that, you get nothing. If we give it just 10 and we're using the positive message function, it's going to guess you're positive. If we give it just a negative, it gives you, nope, you're a negative. And if you give it nothing again, it gives you nothing. But once again, notice it's wrapped in those kind of constructors. So we would probably want to use with default or something like that. JavaScript actually has maybe, but it's its own library. So I didn't even dare to put all the code on there for you to implement a maybe in JavaScript, but you can actually use it. Once again, a little bit uglier, but you can use maybes in JavaScript. And I would probably recommend you do that. Lists. Lists are pretty straightforward. This is just a simple list, returns a list. We create the list 1, 2, 3, 4. If we want to insert something into that, we use that little 2 colon notation there. We're just prepending a num, right? So insert in, we're going to prepend num to our list. So in the first case, we're going to prepend 10. So we get 10, 1, 2, 3, 4. This one, 3, 3, 3. So we get 3, 3, 3, 1, 2, 3, 4. Right? That's how and there's functions to add it to the end, the beginning, insert it into a specific location. All those functions exist to do it. What about loops? We don't have them. We use functions instead. And this is back when I was saying getting comfortable with passing functions around. You don't loop through your data structures, you apply functions to your data structures, and that includes lists. So we're going to start with a fold. In a lot of languages call this a reduce. I'm going to go through this really quick because there's an entire presentation on folds tomorrow. So if this is new to you, I'd definitely go check that out because folds are very, very important in these languages. So go deep dive folds. Okay, so this looks hairy. Whoa. Sorry, gotta get juice. All right, we're good. Okay. We got this higher order functions thing where we take a function. In this case, it said we wanted a function that takes in an int, a list of ints, and gives us back another list of ints. Okay? And then takes in some value to accumulate into. Something that can be accumulated into is like a list or a string. A string can keep adding stuff to it. A number, you can keep adding numbers to numbers, right? That's what they say when they say an accumulator or something like that. And it also takes a starting value. We need to start from somewhere. So here's what we're going to do. We're going to give it our cons thing again, which is the prepend function we mentioned earlier. So all that is that's the type definition, but all it does is take your item and stick it in the beginning of the list. So all that 2 colon thing means. So we're going to give it that function. This is called an infix, where you use a symbol instead of a function. Elm does a little. This is one of the few places they do it. Things like PureScript and Haskell do it all the freaking time. So we give it that function. We're going to give it our initial value, which is this empty list. or our accumulator value, excuse me, an empty list, and then our initial value, which is the list with 1, 2, and 3 in it. So that middle empty list is the one we're going to accumulate into. So takes a function cons, insert at 0, as well as an empty, and of course our starting list, and we're going to fold through it. And there's two types of fold. There's fold left and fold right. We're going to fold left first. What that means is we start on the left, and we're just going to walk our way through it. We're going to fold down. So we take that first on the left, we're going to prepend it to our empty list, and now we have a list of 1. And we have the next value, 2. We prepend it, right? So now it's 2, 1. And then we take that last value to 3, so now it's 3, 2, 1. So we have officially accomplished creating a reverse function. Right? That's all we did there, is we folded down and accumulated in, and our accumulator function was actually just a prepend. You could think if we would have given it a plus sign, and instead of an empty list a 0, it would have added all those together for us. And fold right is the exact same thing, but the other way. So we would start on the right side of our list. So start with the 3, insert it, then the 2, and then the 1. So in that case, we literally did nothing. We got our same list back. Python has this as well. Once again, from our good old friend Func Tools, we have reduce. This is the same code. You can give it an insert function, an empty list in our array, and we get back our reversed list again. So if you've heard of map reduce, that's map fold. Reduce is just a specific version of fold. JavaScript, same thing. They have this thing called reducer. You can do all the same fun in JavaScript. So we can, of course, pass in different functions here. We can pass in a max function. Same thing. It's just going to work down. Right? In this case, our max function is just a simple comparison. If it's greater than the other, give me back that. Right? So in this case, it's going to be 3. This is kind of a dumb use for this, but you can do it. But we can then make a nice function to get a maximum integer here. So if you give us an empty list, we can give you 0. If you give me a list with 1, so that's once again pattern matching, and you're literally pattern matching against the structure of a list, right? And here are our things that can be in a list. We can have an empty list. In that case, I want 0. You can have 1 item in the list. In that case, I'm just going to give back the item. Or what this fancy thing is doing, remember our 2 colon, first thing in the list, rest of the list. That's all that's doing. So now in our function, we're going to call back into our fold with that first item from the list as our starting value, and the rest of the list is the list we're going to pass in. So we just deconstructed, that's what they call that when you pattern match something like that. We deconstructed it into pieces we can reuse. But I kind of hate this function, because if we give it an empty list, we get 0. I don't like this. This infers something. Right? This isn't obvious, because there could just be a list with 0 in it. A list with 0 is not the same as an empty list. And since we're in functional languages, we do things like use a maybe. So instead, we would do something like this. We're just going to say we don't need to even match on the 1. We can take care of that with our top level match. So we're just going to take that, do our max. But if you give us anything else, which in this case is just an empty list, I want nothing back. Then it's obvious, right, that you gave me an empty list because I got back nothing. Our code should be obvious. That's the whole point of all of this, is for things to be obvious. But if you are the type of person who wants to get 0, just give it as a default. So now you can do with default 0, maximum int, and if you'll get back your 0 for an empty list. And that's a way to do function composition in Elm. But that leads us to looking a lot like Lisp, where we'll start having parentheses everywhere, and we don't like that either. So thankfully, Elm gives us some symbols to make that a little bit nicer. So we can do something like this. In this case, Elm's symbol for allowing us to do that is the arrow and the bar. So we're just taking the maximum int function and taking the result and pushing it into our with default of 0. So that's a way that we're just chaining 2 functions together there. With default takes the result of maximum int as its last argument. Yes. So this allows us to do some nice chaining, and by the way, they have the other way. So we can do, once again, the left way, but then they also have the other way where you go into those functions. So you can go back and forth both ways. This will make your code a lot more readable. And then lot of times you'll actually see it like that where you break it on each line, so then it's very readable. We're going from this function to this function to this function. So let's go back and make our fold more generic. We got rid of all those ints, and we made those all A's and B's now. So now it can work with many different data types. And why would we do that? What can we do with a generic fold? Pretty much everything you find in your list module is using a fold under the covers. Map is using a fold. Right? So that map we used earlier, you can use a map on a list where you just map a function to every entry in the list. And below, that's just using a fold to do it for us. So in this case, we're going to map add 1, so 1, 2, 3 becomes 2, 3, 4. JavaScript and Python both use map. These are very common in those languages. Same type deal. I don't know if they use fold to implement them. I have no clue. And like as I mentioned, there's just tons of these functions in the Elm library, and everything you're used to in any of your other languages is empty, linked, reverse, member, head, tail, filter. They're all there. Immutability. Elm is functional and immutable, so we can store and mutate state, maybe? Yes, but we have to use a let expression to do it. So you can actually assign variables here. I think a lot of times when people hear pure language, they think of all these things that means they can't do. It's like, well, no, there's just different ways to do them. So you can assign variables here and actually keep state around. So this is a case where 24 is just 3 times 8, 16 is 4 times 2, and then those two arguments are used in this function here of addition. So it's, when you see in Elm a let and then an in, you're probably assigning a bunch of variables in the let. Those can call into functions, those can do whatever, and then you pass those to the function that's underneath the in. But of course, you can't reassign the same variable. You can't have 24 equal to 3 times 8 and then 24 equal to 20 plus 4. You will get a big, nasty compiler message. But actually, they're not nasty compiler messages in Elm. They're actually very friendly compiler messages. It will actually tell you, hey, you should probably just go rename that, or maybe you did something you didn't want to do. So in our case, we're going to call it new 24, and you can use the new 24.
So Elm doesn't have anything like inner scope variables, including outer scope variables?
I don't know about the actual like naming. You don't do that very often. You don't really use globals in Elm that much, so I can't think. I think they're probably scoped to the let. So you could have it be named at a global level, because it's just going to treat those as different entirely. But within the same let, you definitely can't. So a couple other quick notes on let expressions. You can assign functions, and you can even provide type annotations in those. So here we actually have functions, hypotenuse function equal to square root. That one doesn't have a type annotation. This one below has type annotation, and this other one has a type annotation. And as you can see, you don't actually have to use all those variables if you don't want to, but once again, you probably should because you don't want dead code around. This isn't very common where you'll actually define functions within there and the types. You usually keep your functions outside at the global level and call into them here. This is kind of another way if you don't want to chain a bunch of functions. Another way to do it is to set them to variables and then call it in later. So those are really the basics of Elm syntax. But if you're nervous, don't worry. You've got the compiler. In every other language, I would say, oh God, not the compiler. Except in Elm. Elm is the first compiler I've met that I like. Don't fight it. Let it help you. You don't even have to provide the types. The compiler will tell you the types. So this, our update from earlier, if you compile your Elm code with this in it and you tell it to show you warnings, it will warn you're missing a type annotation, and it will give you the type annotation. Not only that, it will tell you when you're being a little too strict. Actually, you don't need to make it from that thing to that thing. You actually can just do our records we showed earlier where you just need a record that has a value event on it. So we even give you the most specific type you need. So I highly recommend this if you're new and beginner. Don't worry about the types. Just write the code like you normally would. And let the compiler help you. And start simple, keep compiling, compile often.
Can you talk about reading signatures out loud to help you?
Sure, so that one is, so that's an update function that takes its first argument of type message. It then takes a second argument of type and a record that has a value of int on it. And then it returns us a tuple in this case. And I haven't showed you tuple yet, but this is what a tuple would look like. is just the parens with a comma delimiting it. So kind of like how we showed list earlier with the bracket, the square brackets, it's just parens here. So in this case, we're going to return a tuple with the first value being a record that at minimum has a value of an integer on it. And then this thing called command message, which I'm not sure if I'm going to have time to get to, but is a built-in Elm type command. So Elm compiler is really helpful. Don't fight it. Don't attempt to outsmart it. Just write your code. Let the compiler lead you where you need to go. Just get it in and compile. OK, so one last thing, debugging. This is actually another one of the big things, especially in Haskell and PureScript, will throw people off, is doing some debugging things, especially this guy. In other languages, just logging out what the hell is happening in my system is actually kind of difficult. You have to know what a monad is to do that correctly. You don't know. They cheat to get away with it. What Elm actually does with this log function is it calls into JavaScript where rules don't matter, and then comes back. So that's how they cheat the system. So let's walk through how we actually use this. So this log, it literally does nothing to your function. You can wrap everything in this log, and it's just going to take whatever you gave it and give it back to you. But in the meantime, it's going to put that into your console. Right? So, and this can be anything because it hands it to JavaScript, and JavaScript will try to crap anything out to the console as long as you give it to it. So that's all they do is they say, JavaScript, take care of it, and then we'll come back and do the rest of it. So in both of these, right, it's going to log out the value, but actually not change that value. It is not pure. It cheats. But you can use it. So let's say this is a more realistic looking thing. You could do something like this. You could put it in a let statement. And here we're using the underscore again to say we're not even going to set it to anything. We don't give a crap. I'm just logging my stuff out. Right? You'll see this a lot in beginner code. Just, God help me, what is going on here? Log it out quick. Right? And that's the quick way to do it. But you actually don't even have to do that. We can even wrap it in our case statement around the action itself, because remember, it's a pass-through. It doesn't care. It's just going to take that action and pretend like that log statement's not even there. And the case statement's going to behave normally. The JavaScript will take care of putting it in the console for you. And there is another thing called crash, which is very similar, except it's actually going to break your crap. So it's going to blow the system up and give you errors. So use this when you're writing your code. Do not use this when you're shipping your code. Elm architecture. Let's go through this really quick because I think it's important. Model, update, view. We've seen this. The model's the state. The update is the way to update your state, and the view is just your HTML. Looks something like this. Model renders view, sends message to our update, comes back to model. That's the Elm architecture in its simplified form. This is very helpful because it helps us with side effects. The last big elephant in the room. Historical FUD. You can't build anything in real functioning programming because it's pure. Then it came along this dude. And the first time we're going to mention monads. He found out you could use monads to handle side effects, which is why you see this thing, IO parens. It freaks everybody out. And you start seeing code that looks like this with the IOs and all these symbols, and oh my God. Hopefully this doesn't look quite as crazy. But this tends to be the thing that freaks people out. PureScript, F. These are more monads. You'll start seeing stuff like this. See that console? That's the only way you can log crap out in PureScript. You got to learn monads to do it. That's what freaks people out. This is an update function in basically the closest thing to the Elm architecture in PureScript. So this is kind of their version of the update function. You can see it's more complex, very powerful. Right? This is the trade-off. These are very, very powerful structures, but they're more complicated to understand. Elm doesn't support it. Yay. All side effects are handled via the architecture, via task and effect managers. Thankfully, you likely won't ever have to write an effect manager. Elm's goal is to provide them for you, but you can if you want. So let's actually walk through this quick. Elm uses commands for side effects. You trigger a command, which will then trigger its actions as part of its side effects. So you end up with something like this. We just have this extra part of our architecture. So the update could trigger a command, which goes into the Elm runtime and triggers a message, which comes back into our architecture. So let's actually walk through this quick. We're going to build this guy that just loads us some GIFs. Every time we click the button, we just get new cat GIFs. By the way, all of this is from the Elm documentation. This is the first tutorials you will do if you go do the Elm stuff. which is why another reason I like the Elm things, you do real things you might actually do. Maybe not loading cat GIFs, but you're certainly going to make HTTP calls in your front-end code. So let's do it real quick. We're going to create a model. We're going to store our topic and the URL for the GIF. You can see now our init, instead of just returning a model, we're returning this command thing. But in this case, it's just a none command. We're saying we don't have a command to trigger yet, right? And I just showed the picture. The command is going to do something off in the bad world. So, but in this case, we don't have anything. We're not going to do it yet. Here's our view code. This should look familiar. When you click the button, it's going to trigger a more please message, which is right here on our message. More please. But you see, we now have this new GIF action. And then it takes in a result. I showed you the result type earlier. And this result either has an HTTP error or a string result. So our OK is a string. Our bad is an HTTP error. And that's the type of result we will get when we trigger the new GIF action. So we're either going to get back a string or an error. And that's what we pattern match on. So more please was our button. So that's going to call into a function, get random GIF, and I'll show you that in a second. But once that guy gets done and goes through the architecture, he's going to send us that result. And all it does is come back into our same update function that we were in earlier. And we're just going to pattern match. But now you see we have two new GIF patterns, even though we only have one message. Well, once again, it's breaking down the structure. That has a result object. So the result either returns an OK or it returns an error. So now we got to match against that as well. So you can nest kind of the way you match. You could do that underneath. You could have a separate case. So you could just match the new GIF and have a separate second case under it that only matches the OK and the error. But you can also do it all in one at the top level. So in this case, we're bad programmers. If we get an error, we're just going to blindly swallow it. We're going to return our model and do nothing.
If you omitted that third case, the file would
It would tell you that you need to handle your error case. In this case, we're handling it poorly, but it would be handled and you would know that you handled it poorly instead of, oh God, I didn't handle it. So here's our get random GIF. So we got a URL. We're going to call into our giphy.com. Our URL, we create a request. That http.get is just creating a URL request that takes our URL and then this decode function. And this decode function, we're actually going to get back some JSON thing. And this is just going to help us break that down and get back just the image URL, which is what we want in this case. If you go through the example, or the tutorial, they'll walk you through that much more. But really, this is about as complicated as a lot of front-end back-and-forth gets. JSON decoding, HTTP requests. And that's what everything's doing there. So we create the request, set it to the request variable, and then we send it in. And you see that new GIF is our command again, right? So that new GIF. So we're telling our HTTP send that trigger the new GIF command or message action with this request. And that's what we're doing with that send. So new GIF comes from our message, and we're going to pass it the request that we created above. And these are the type definitions for HTTP GET and HTTP SEND, just so you can see those. And that, once again, going back, that is all the code to do that. And that's what I just broke you through. I'm technically out of time, so I can't get to my last one, which was showing you a clock ticking. But I guess I could show it here. Ticking clock. The only new thing I will call out in there is it uses this thing called subscriptions, which I suppose I can show you the slide for that quick, just so you can see how that fits in. So you can also, as well as triggering commands, you can subscribe to commands. And that's what it's doing here, is it's actually subscribing to a time command. So we just passed that in our update. We got a subscription, and this is the subscription stuff. So in this case, we're saying every second we're going to trigger a tick message. Those are the type definitions for the every, the second, the tick. And this is now how our architecture looks. So you can subscribe, so it comes around. So this is how you will handle reactive type things, right? Interop, getting the dimensions from the window, right? You will subscribe to the resize function of the window, and every time they resize it, it'll actually trigger a function for you. Yep, and JavaScript interop, it can do that too, and I don't have time to go through that. Where we are. And it's actually, it's using subscriptions. You actually subscribe to JavaScript functions, and you trigger them via commands. Same way, same exact same thing. So that is all I have. Thank you. And here's some resources. I told you I don't learn well from books. The single book I highly recommend is Haskell from First Principles by Chris Allen, who's running around this place and doing teaching. That is by far, I think, the best book for Haskell, Elm, PureScript. It doesn't matter. That book teaches you all of it and do all the exercises. It'll take you a year. I'm not kidding. But go do Elm, ship your stuff to production, do the book, and then you can come back and switch everything to PureScript and Haskell if you want down in the future. But legitimately, that book is the one that's going to teach you the monads and the frees and the functors and all of that stuff that we actually used here. By the way, we were using all of that. We just didn't call it out.